Welcome everyone. I am Tanushri Dalai from Civil Engineering branch. So in the last class, we discussed about the numerical based on compressive member. So today, we will start the calculation of compressive strength of the compression member. So for that, we need to calculate the FCD, which is compression stress value, or you can say the compressive stress value. So to find out the FCD value, we need to calculate two factors. First one is your phi and second one is your lambda. So as we know that this particular I section undergoes the buckling class in ZZ axis, which is A, and in buckling axis of YY axis, for which the buckling class is B. So we have to find out the two values of compression strength of the I section. First one is in your ZZ axis and second one is in your YY axis. So while we calculate the slenderness ratio in that part, while we calculate in case of ZZ axis, we put the length by effective length by radius of gyration. In that place, we will put the radius of gyration in ZZ axis, and while we calculate the slenderness ratio for the YY axis, we need to put the radius of gyration in YY axis. So first of all, we are calculating the compressive strength in YY axis. So for that, we put the FCC value directly in the formula of lambda. So we know that lambda equal to Fy by FCC whole root over. So here the FCC value is pi square E divided by slenderness ratio to the power 2. So directly we put this value here. Then by putting the values of Fy, KL, RYY and E, we got the value of lambda as 0.654. Then next factor is your phi. So we know that phi equal to 0.5, 1 plus lambda, then alpha into lambda minus 0.2 plus lambda square. So we know that in case of buckling in YY axis, the buckling class is B. So for buckling class B, the alpha value is 0.34 from the table number 7. So we put the value of alpha here, and by calculating all these things, we got the value of phi as 0.971. Hence, we got the value of phi as well as lambda. So we can calculate the FCD value by putting the value of Fy, gamma m0, phi and lambda. So by putting the value of all these things, the value of FCD is coming out as 183.86 Newton per mm square, or easily megapascal. So now we can find out factored axial load, that is the compressive strength of the compression member, which is denoted as PD, which equal to AE into FCD, where AE is the cross-sectional area of the I section and FCD is the value which we have already calculated. So the AE value is 10466 and FCD value is 183.86. So the total value is 1924.28 into 10 to the power 3 Newton. By converting this into kilonewton, we need to divide 1000, by which we got the value 1924.28 kilonewton. So this is all about the buckling along the YY axis. So in the second part, we need to calculate the value of PD while the I section is buckled about the ZZ axis. So in the similar process, first of all, to find out the FCD, we know we have to calculate the phi value as well as the lambda value. So the lambda equal to Fy by FCC whole root over, and here also we put the value of FCC directly in the formula of lambda. So here in the slenderness ratio we put the RZZ, that means the radius of gyration along the ZZ axis. So by putting the value, we can find out the lambda as 0.203. Similarly, to find out the phi value, we need to put this formula, and here the buckling class is A. So for buckling class A, the alpha value is 0.21. So by putting all these things, we got the value of alpha as 0.521. So now we have the value of lambda and phi. So we can put this value to calculate the FCD. So by putting all the values in the FCD formula, we can find out the FCD as 227.085 Newton per mm square. Hence, the last step of the method, which is to find out the factored axial load, which is PD equal to AE into FCD. So we know the AE value. So AE equal to 10466 and FCD we got 227.085. So by multiplying these two factors, we got the value 2376.67 into 10 to the power 3 Newton, and by converting this Newton portion into kilonewton, we can divide 1000 in the value of 237.67 into 10 to the power 3, by which we can got the PD value as 2376.67 kilonewton. So in this way, the factored axial load for the I section in the buckling about ZZ axis and YY axis is finished. Now, we will solve another numerical which is based on a compression member, that is channel section. So the question is, design a column section using channel section only to carry a factored axial load of 400 kilonewton. The column is 4 meter long and is effectively held in position at both ends, but restrained against rotation at one end only. Consider Fy equal to 250 megapascal. So this question is one type of different kind of question, because in this question the type of section is not given. Only this question mentioned that we can only use the channel section and the factored axial load is given. So this is the clue to find out the section of the question. So from the 400 kilonewton, we can find out the type of section for this particular question. So basically, first of all, we need to find out the permissible design compressive stress, which is constant for the angle I channel sections. So we know that stress equal to force per unit area. Hence, area equal to force by stress. So the 80 MPa is the value of design compressive stress, which is common for all the compression member except built-up I-bar. For the built-up I-bar, the value of design compressive stress is 100 MPa or 110 MPa. So here, for the channel section, we will use the design compressive stress as 80 MPa. So, we have the factored axial load, that is load is given, and we assume the design compressive stress as 80 MPa. So by the help of these two factors, we can find out the A required. So area equal to load divided by stress. So here the factored axial load is converted into Newton. So we multiply 1000 here and divided by 80, which equal to 5000 mm square. So we got the value of A required is 5000 mm square. Then as per the area required, we know that for the design purpose, that may be in concrete or maybe in steel, while we will provide an area for limit state method, we always use the area provided, which is always greater than the area required. So, your provided area should be more than the required area. So, based on this theory, the area provided for this particular question, we need to put the area which is greater than 5000 mm square. So as per the area required, we need to find out the section that is already given in the question. We can only use the channel section. So in the steel table, we can find out the area which is nearly greater than 5000. Hence, we will get a value of area which is 5366 mm square, and this area is for the section ISMC 350 at the rate 413 Newton per meter. So in this way, we can find out the section from the factored axial load. So today this much. We will solve this question in the last class.